Hello, this is the lecture for linear systems. All right, we should start at the beginning. What is a system of equations or a linear system of equations? In general, a system of equations is a collection of two or more equations with two or more unknowns or variables. To solve the system of equations, we solve for those variables simultaneously. The solution to the system, of course, is the values that make all of the equations true, the values for the variables that make all of the equations true. All right, so conceptually, that's what a system of equations is. In general, you need to have at least as many equations as you have variables that you're solving for. Right? Let me say it again. You have to have at least as many equations as you have unknowns or variables that you're solving for. So if you're solving for two variables, you need at least two equations. If you're solving for three variables, you would need at least three equations, so on. All right, there are multiple methods for solving systems of equations. We're going to talk about three of them shortly. The first method is by graphing the equations. We're in the unit on linear equations here, so we're limiting ourselves to lines. The system to the solution to a system of linear equations is where the graphs cross each other or where the lines intersect. Okay. The second method we'll look at is the substitution method. This involves solving one of the equations for one of the variables and then substituting that new expression into another equation. The third method that we'll look at is the elimination method, and that's sometimes referred to as the addition method. This method involves adding the equations together such that one of the variables will add out. And often we have to multiply one or more of the equations by some value so that when we add them together, one of the variables adds out. Okay, a fourth method is using matrices to solve systems of equations. We aren't going to look at that in this course. That's outside the scope of college algebra. But I do want to mention it. It's a valid method for solving systems of equations, and it's probably the only practical method that can be used for larger systems where there are perhaps four or more variables and four or more equations. All right, let's look at the first method, solving a system of equations by graphing. All right, here, in fact, predominantly we're going to look at systems that are limited to two equations with two variables. Here we have two equations, and there are two variables, x and y. The solution to this system of two equations here is going to be the value of x and the value of y that makes both equations true. All right, but to solve this by graphing, we're going to graph each equation, and where the two lines intersect is the solution to the equation. All right, so to graph these, I think what I'll do is I will convert them to slope-intercept form and graph them that way. So for this first equation, if I wanted to solve for y, let me just rewrite it. We have negative 5x minus 4y equals 2. Solving for y, let me add the 5x to both sides first. So then I have negative 4y is equal to 5x plus 2. And then I'll divide everything by negative 4. All right, so solved for y, this equation becomes y equals negative 5/4 x, and then plus negative 2/4, that reduces to 1/2, so minus 1/2. All right, to graph that line, I now have it in slope-intercept form. The intercept, the y-intercept, is negative 1/2. So that's 1 point on this line. I'll use the slope to find the second point. The slope is negative 5/4, right? So that's either, if I do rise over run here, that's either negative 5/4 or it's 5 over negative 4, either way, for my rise over run. So if I start at this y-intercept and I go down 5 and right 4, I should get a second point. So down 5, 1, 2, 3, 4, 5, and to the right 4, since 4 is positive, 1, 2, 3, 4, there's a second point on that line. I could also use positive 5 over negative 4. Let's go back to the y-intercept and we'll go up 5, 1, 2, 3, 4, 5, and left 4. 1, 2, 3, 4, and there we go. There's another point. All right, I could do that again if I wanted to, or I could just get my straight edge, connect these points, and I'll have that first line. All right, so there is the line negative 5x minus 4y equals 2. All right, now let's graph the second line, and we'll do that one in pink. All right, we'll solve for y, so let's subtract that 4x from both sides. So the second line then, when solved for y, is y equals negative 4x plus 5. Okay, in slope-intercept form, 5, y equals mx plus b, right? That's our slope-intercept form. 5 is my y-intercept. So that's one point that's going to be on this line. And my slope is negative 4, right? So if I'm doing rise over run, that's going to be either negative 4 over 1 or 4 over negative 1. All right, let's count that out. Let's do negative 4 over 1 first. Negative 4, down 4, 1, 2, 3, 4 to the right 1. Maybe I'll do it again. Down 4, 1, 2, 3, 4 to the right 1. Okay, I could also use the 4 over negative 1, so let's go up 4, 1, 2, 3, 4 to the left 1. That's probably enough lines, enough points. Let's connect those points with a line now. And there's our second line, 4x plus y equals 5. Okay, the solution to this system of equations is where these two lines intersect, and it looks to me like it's this point right here. Now, I think the total numbers, the coordinates of that point are 2, negative 3. X is 2, y is negative 3. But here's the weakness in solving a system of equations by graphing. When you're sketching it by hand, sometimes it's difficult to see the exact value where the lines intersect. In solving by graphing, you often will want to use a graphing calculator or an online graphing calculator like Desmos. If we do it that way, we can be certain that we know the exact values of where those lines intersect. It's not necessary that you have a graphing calculator, but if you do, I'll show you how we could graph these two lines and find the solution to the system of equations. All right, so first thing I'm going to want to do is clear out some things I had in there previously. I'll press my y equals to enter the first equation, okay? The first equation, when solved for y, is y equals negative 5/4 x minus 1/2. Okay, so let me type that in. See, I'll need parentheses here. I could put the negative in front of them, I guess. Negative 5/4 x minus 1/2. To use the parentheses around these fractions if I want to put them in there as a fraction, because the calculator is not smart enough to know. For example, that I want to subtract 1/2. The calculator is not smart enough to know that I want to subtract 1/2 without the parentheses. It would think I was subtracting 1 and then dividing by 2. It would use the order of operations strictly as they're presented. All right, so there's our first equation. Now let's put the second one in. Y equals negative 4x plus 5. That's our second equation. Okay, I'll hit my graph key to graph them. And there's the first line, There's the second line, and I can visually see where they intersect. It looks like it's about at 2, -3, but to find my exact value, I have a function in this calculator that will tell me if I hit the second key and then the trace button that says calc, okay, and I move down here to intersect, it's going to tell me the exact intersection of these two lines. I'll press enter. Okay, it's asking me which is the first curve or line that we're using, because it doesn't have to be lines. We can also intersect other types of graphs. So it's linking right there on this one, so I'll press enter. Now the second curve, it's assuming I mean this one, and I do, so I'll press enter. And then it's saying, shall I guess now? I'm going to say yes, and I'll press enter one more time. Now we can see that the intersection of those two lines occurs exactly at x equals 2 and y equals -3. Okay, so we use this graphing calculator, and Desmos will do the same thing for you, desmos.com online. That's a free graphing calculator, to confirm that the intersection is in fact at the point that has the coordinates 2, -3. X is 2, y is -3. Okay, so there's the first method for solving a system of equations by graphing them. The second method is to solve them by substitution. It's referred to as the substitution method. With this method, we're going to solve one of the equations for one of the variables, and then we're going to substitute that new expression into the other equation for that variable. All right, so which equation should I work with? Well, I'm just going to choose the easiest. I think the easiest thing to do here is to solve the second equation for y, because I only have to do that in one step. If I just move that 4x over, then I have that equation solved for y. So let me do that. I'll just subtract the 4x from both sides. Okay, and then that gives me y equals -4x plus 5. Okay, now I have this expression for y in terms of x, right? So I can take this expression for y and substitute that in to the other equation where I see y. So we'll substitute it in right there. When I make that substitution, after I make that substitution, I now will have an equation that only has one variable in it, x, namely x, and I'll be able to solve for x. All right, so let's go ahead with that. When I make that substitution, maybe I'll just continue in pink here. What I end up with then is -5x minus 4 times, and instead of y, I'm going to use this new expression for y. So it'd be -4 times -4x plus 5. All right, and it still equals 2. Okay, now all I need to do is simplify and solve for x. So let's distribute that -4. We can drop those parentheses. Okay, so we'll have -5x. -4 times -4x is +16x, and then -4 times +5 is -20. That equals 2. Let's combine these like terms. -5x and 16x is 11x. Okay, let's move that 20 over, so we'll add 20 to both sides. Go up here to finish. So then 11x is equal to 22, and divide both sides by 11, and we see that x is equal to 2. Okay, now that we know the value of x, we can use that value in either one of these two equations, or the one where I solve for y. Any of these equations, I can use that value of x to find the value of y. Randomly, well, you know what, I think it'll be easiest to use this equation here, so I'll probably do that. So I'm going to take this 2, and I'm going to substitute it in there for x, right? So then y will be equal to -4 times 2 plus 5, which of course is -8 plus 5, or -3. Okay, so our solution here then, x is -2, y is -3, so we write that solution as an ordered pair, 2, -3. Okay, now we were solving the same system of equations as we did with the graphing method. So of course we would come up with the same solution. That makes sense, right? So there's the substitution method for solving a system of equations. The third method that we want to look at is the addition or elimination method. All right, let's look at the same system of equations, but let's solve it this time using the elimination or the addition method. All right, with this method, our goal is to add the two equations together so that one of the variables adds out. Now, if I just add these two equations like they are, though, none of the variables are going to add out, right? If I add negative 5x and 4x, I get negative x. If I add negative 4y and y, I get negative 3y. But I don't want that to happen. I want either the x terms to add out or the y terms to add out. So I'm going to need to multiply one or maybe both of these equations by some constant so that when I add them together, one of the variables will add out. Now looking at these, which equation do I want to multiply? Which variable do I want to try to add out? Well, you could work on adding out the x or the y. Looks to me like eliminating the y is going to be the easiest, right? Because if I multiply this lower equation by 4, right, I'm going to have a negative 4y and a positive 4y, so they will add out. That looks like the easiest. But I could have also said, well, maybe I'll multiply the top equation by 4 and the bottom equation by 5. Then I would have had negative 20x and positive 20x, and the x's would add out. But that involved a little bit more work. I'm going to go the easy way. I'm going to do it this way. So let me rewrite that. Let's distribute that 4 to the entire equation. So then I have negative 5x minus 4y equals 2. We just recopy that first equation. And the second equation becomes 4 times 4x, or 16x, plus 4 times y, that's 4y, equals 4 times 5, or 20. Okay. Now when we add them together, the y terms add out, right? And negative 5x and 16x is 11x. 2 plus 20, of course, is 22. Divide both sides by 11, and I see that x equals 2, as expected, right? How do I find y? The same way that I did with the substitution method. I'm just going to substitute this x into any of these equations. I don't know, maybe I'll just use this lower equation here because it's the closest one to the x. I'm just randomly choosing this guy this time. Doesn't matter which one I use. So this 2 will go in there for the x. Right? So then we'll have 4 times 2 plus y equals 5. 4 times 2, of course, is 8. Subtract that 8 from both sides, and I see that y equals negative 8 and positive 5, or negative 3. So we have the same solution here as expected, where the ordered pair that satisfies the system of equations, or the ordered pair that makes both of these equations true, is when x is 2 and y is negative 3, right? Should we check that just for the heck of it? Yeah, let's plug them back in just to prove the point. Okay, if x is 2 and y is negative 3 for this first equation, then negative 5 times 2 minus 4 times negative 3 should equal 2. Well, negative 5 times 2 is negative 10. Negative 4 times negative 3 is positive 12, and negative 10 plus 12 is definitely 2, right? We can check these values in the second equation here as well. 4 times 2 plus y was negative 3 should equal 5. Well, 8 plus a minus 3, that's 8 minus 3. 8 minus 3 is definitely equal to 5. Okay, so there's our 3 methods. We can use any one of those 3 methods to solve a system of equations. The graphing method is more valuable when you have access to technology, like a graphing calculator or Desmos, for example, on the computer. But you can sketch it by hand as well. The substitution method and elimination method are important when we don't have access to technology and we need an exact answer. They involve decimals. Right? Decimals are fractions. And then choosing between substitution method or elimination method, it's kind of 6 one, half dozen the other, but sometimes one method will be easier than the other method. All right, here's another example. Let's take a look at this example here. This one is kind of interesting. This one is really interesting. Which method should we use to solve it? Well, we could use any of the methods, but I think I'm going to use the addition method, elimination method, because I'm quickly seeing a pretty easy way to do it. If I multiply that top equation by -3, I'll have -3 times 2, or -6x, then I'll be adding to +6x, so my x terms are going to add out. So let's just go ahead and rewrite that. And -3 times 2x is -6x, -3 times -3y is +9y, and -3 times 4 is -12. So that'll equal -12. All right, then let's just copy the second equation. 6x minus 9y equals 36. Okay, when I add these together, -6x, +6x, they add out, or they add to 0, right? Negative or +9y and -9y, they also add out, or they also add to 0. And -12 and +36 add to 24. Well, this is interesting, isn't it? Well, the x terms and the y terms added out, and we ended up with this equation that isn't even true, is it? Is 0 equal to 24? Absolutely not. Not in this universe. Not in this universe. 0 is not equal to 24. So what does this mean? What does this mean? Well, this means that there is no solution, right? 0 does not equal 24. There is no solution here. In fact, if I were to graph these two lines, they would be parallel lines. They would be parallel lines. And they would look, let's see if I can in my head just give you a rough estimate of what they look like. I don't think I did graph these. They're going to have a negative slope. They'll look something like this. They're going to be parallel lines. They never intersect, so there is no solution. No solution at all. Or we might call these inconsistent, an inconsistent system. It does not have a solution. All right. Now let's take a look at this example here. Looks similar, but a little bit different. Well, let's see. How can we solve this? Let's try that same method, that elimination method. Look at the 2x and the 6x. I think if I multiply that top equation by -3, I'm going to have what I need to add out the x term. Okay. So -6x plus 9y equals -12. That's my first equation when I distribute that -3. Right? Let me copy over that second equation. 6x minus 9y equals 12. And let's add them. This is interesting, isn't it? Look, -6x, +6x, well, that's 0. +9y, -9y, that's 0. -12 and +11, that's 0. So we end up with 0 equals 0. Is that true? Sure is. It's always true, isn't it? Doesn't really matter what x and y are. This equation is always going to be true, no matter what values we put in there for x and y, because they add out, right? They add out. So what does that mean? What does that mean? That means that these are actually two versions of the same line, or really just two versions of the same line. If we were to graph that first line, it would look something like this. If we were to graph that second line, it would be right on top of the first line. It's actually the same line. It's actually the same line. So we would say here that we have an infinite number of solutions. Okay? Any solution to the first equation, any ordered pair that makes the first equation true is also going to make the second equation true. Right? So any x and y combination that make one equation true will also make the other equation true. And there will be infinitely many ordered pairs because, of course, a line goes on forever and ever, and every point on that line can be represented by an ordered pair. All right, so we have a nice summary on the next page here. A nice summary of what we just discussed. If we have a situation where there is no solution to a system of equations, it graphs as parallel lines. They never intersect, right? And we refer to this as an inconsistent system of equations. Okay? If we do have a solution to a system of equations, we would call that a consistent system. Okay? And it may have one solution, okay, which would be an independent, consistent but independent system of equations. And that's where there's one solution. When we graph lines, they intersect in one point. Or we may have an infinite number of solutions. We may have a consistent but dependent system of equations, meaning that if we graph the systems of equations, they actually graph to the same line. Each equation in the system, when we have dependent systems, is just a multiple of the other equation, the other equations. Okay, so there we have the three methods for solving systems of equations. Now that we've talked about the nuts and the bolts, let's take a look at some applications. Applying these concepts can be a little bit tricky, or using systems of equations to solve a problem. It can be a little bit tricky, it can be, but there are some structures that we can use to help us formulate the equations that we need to solve the application. So many applications that involve systems to solve them can be thought of as a mixture problem, right? A mixture problem is one where you have a quantity equation and a value equation. So if I can look at the application and think about a quantity equation and then maybe a value equation, write those two equations, that would give me the system that I then need to be solved, that I then need to solve. Also, it's important to note that it can be helpful also to draw a table or chart to parse out the data. All right, let's start with a pretty straightforward application. Here in this example, Sue has a combination of nickels and dimes. The total number of coins that she has is 25, and they total their value totals $1.50. How many of each coin does she have? All right, well, if we think about this as a mixture problem, I think we can, because we've got a mixture of nickels and dimes, right? So it seems like a mixture problem. If we think about this as a mixture problem, then we can use this framework here of trying to write a quantity equation and a value equation, a quantity equation and a value equation. Well, the quantity equation is going to be a quantity of one thing plus a quantity of another thing equals a total quantity. In this case, I think the quantity is going to be the number of coins, right? So let's see. We don't know how many nickels or how many dimes, so we'll need to assign some variables. So I think I'll let n be the variable that represents the quantity of nickels. And we'll let d equal the quantity of dimes. So then my quantity equation is going to be, the quantity of nickels, or n, plus the quantity of dimes, or d, equals the total quantity. The total quantity here was 25 coins. Okay, there's my quantity equation. Now let's see if I can write a value equation. With the value equation, usually, oftentimes, I shouldn't say not usually, but oftentimes the value equation will be represented by money, right? Will be represented by money. In this case, value is money. In this case, the value of these coins is $1.50. Okay, so I want to write a value equation. I want to write the value that nickels contribute plus the value that dimes contribute equals the total value. Well, nickels are worth 5 cents each. So the value that nickels contribute to this equation is going to be 0.05 times the quantity of nickels, right? 5 nickels then nickels would contribute 25 cents toward the total quantity, total value. All right, so nickels contribute 0.05 times n. Dimes, the value that dimes contribute, dimes are worth 10 cents, right? So the value that dimes contribute is going to be 0.10 times the quantity of dimes, right? If I had 5 dimes, dimes would contribute 50 cents to the total quantity, right? So 0.05n plus 0.10d is going to equal my total value, and the total value is given right here. It's $1.50. So there I have it. There's my quantity equation and my value equation. Now I've written a system of equations that I can solve, and I can solve this system with any of the 3 methods. I think this one lends itself nicely to the substitution method, so I think that I'll do that. If I subtract a d from both sides of this equation, I end up with a new equation that says n equals 25 minus d. Right? I just subtracted a d from both sides of that equation. Right? Now, I can substitute this new expression for n into the other equation, right down here. Okay, and I'll have 0.05 times, and instead of n, I want the 25 minus d plus 0.10d equals $1.50. Now I have an equation with only one variable in it, so I can solve for that variable. Okay, so let's simplify and solve for d. Let's distribute that 0.05. Okay, 25 times 0.05 is 1.25. All right, yeah. And then 0.05 times d is just minus 0.05d plus 0.10d equals that $1.50. I have some like terms that I can combine here. So 1.25 minus, let's see, oh, no, plus. Negative 0.05d plus 0.10d is going to be plus 0.05d. And that's going to equal the $1.50. We'll subtract that 1.25 from both sides. Go up here to finish. So then 0.05d equals 1.5 minus 1.25. That's going to be 0.25, and subtracting both sides, or I'm sorry, dividing both sides by 0.05 tells us that the quantity of dimes is 5. 0.25 divided by 0.05 is 5. I don't know why I wanted to check that. My brain is doing being weird today. So we know now how many dimes there are, 5 dimes. To find out how many nickels, we'll just substitute that d, that value for d, into one of the other equations. It doesn't, oh, that's a highlighter. I don't want that guy. Let's try. Go to green. So we want to substitute that d. I'm going to use this nice simple equation here. We'll substitute that 5 in there for d. So n then is equal to 25 minus 5, or 20. Okay, so my answer here is that there are 20 nickels and there are 5 dimes. Okay, check our answer there. Well, let's say 5 dimes, that's worth 50 cents, right? 5 times 10 cents, that's 50 cents. 20 nickels, 20 times 0.05, that's 100, or 1 actually, 0.05. So 20 nickels is $1, so $1.50. Yep, that's exactly what they were supposed to equal. All right, so this quantity and this value structure works very nicely for solving applications that seem like mixtures of things when we're mixing 2 or more things together. Let's look at another example here. Okay. So here we have a movie theater. It's charging $9 for adults and $7 for senior citizens. On a day when 325 people paid for admission, the total receipts, the total money taken in was $2,495. We need to try to figure out how many of those tickets were adult tickets and how many of those tickets were senior tickets. Well, the first question I always ask myself is this a mixture problem? Yeah, I think it is. We're mixing adult tickets and senior citizen tickets, right? Since we're mixing these two types of tickets, I think I want to think about this. I want this to be a mixture problem. Mixing tickets. Okay, so it's a mixture problem. So then I want to try to write a quantity equation and a value equation. That is the framework that works very nicely for solving mixture problems, mixture type problems. All right, so the quantity, what's my quantity going to represent be? What quantities do I have here? I think I have a quantity of tickets, right? 325 people paid for admission, so 325 tickets were sold, right? So I'm going to need to assign some variables. I don't know how many of them were adult and how many of them were senior citizen, but let's see, why don't we let A equal the quantity of adult tickets. And then we'll let, what variable should we use for senior citizens? I guess we'll use S. We'll let S be the quantity of senior citizen tickets. Okay, so our quantity equation then is going to be the quantity of adult tickets, or A, plus the quantity of senior citizen tickets. A plus S is the total quantity. What's my total quantity here? It's 325. Okay, now can we write a value equation? Now when money is involved, usually the value equation is going to be the value of money. It's going to be money. Money and value, they kind of go together, don't they? Money is valuable. All right, well, let's see. There is money involved. $9 for adult tickets, $7 for senior. Okay, well, that means that the total value, let me see what that total value is. It's $2,495. That was the amount of money taken in. So the total value that adult tickets contributed to total receipts is going to be $9 times the quantity of adult tickets sold, right? The value that the senior citizen tickets contributed would be the price of one ticket, right? Or the value of one ticket would be the $7. Times the total number of senior citizen tickets sold, or the quantity, sorry, of senior tickets. That was S. Okay. And then when we add those together, our total value here is going to be $2,495. There we go. So there's our two equations. We have a quantity equation and a value equation. Substitution worked nicely for that last one, and this one's very similar, so I think I'll use substitution again here. Okay, if I subtract an S from both sides, I have A left, so A then is equal to 325 minus S. Okay, and there's an expression for A that I can substitute in to the second equation, right there. So then 9.00, I think I'll just say 9A plus, oops, not A, my mistake there, 9 and my new expression for A. So 9 times, not A, but 325 minus S. Okay, that's a 5. This is an S. Ooh, my variable might not have been the best choice. Plus 7.00, I'll just write that as 7S. And that's going to equal the 24.95. Okay, let's simplify and solve for S. We'll distribute that 9. What is 9 times 325? I don't know. Let's find out. 9 times 325 is 2925 minus 9S plus 7S is equal to 2425. I'm sorry, 2495. Okay, so combine those like terms, those S terms. So 2,925, negative 9S and positive 7S is negative 2S. It's going to equal 2,495. 95. All right, now solving for S, we'll want to subtract that 2925 from both sides. Go up here to finish. So then negative 2S is going to equal 2495 minus 2925. That's going to be negative 430. Okay, we'll divide both sides by negative 2, and we see that S, the quantity of senior citizen tickets, is 215. Okay, now that we know S, it's easy enough to find A, the adult tickets. We'll just back substitute, right? We'll take that value for S into any of these equations. Here's a nice easy one to use. I'll use this one, put it right in there. So now A is equal to 325 minus 215, or 110. All right. So our answer here says that we sold 215 senior citizen tickets and 110 adult tickets. Okay, I can always check that by plugging these values back into both of the equations and making sure that they're true. Let's see, several other applications here. Let's go away from mixture applications for a minute. Let's go away from them. Even though many applications that lend themselves to systems of equations to solve are mixtures, they aren't all. Okay, here's one that doesn't really seem like a mixture problem. What's going on here? This is called a break-even point problem. Well, I don't know what's it saying. The cost to manufacture a pair of jeans is given by this equation, y equals 29x plus 1,000. All right, the revenue equation is y equals 49x. What is the break-even point? Okay, well, this is a business application. Let's talk about this. What does break-even mean? Break-even is when costs equal revenues. Right? If you're in business for a reason, and the reason that you're in business is probably going to be to make a profit. It's probably going to be to make a profit. So the break-even point is going to be very important. The break-even point, we're going to want to make sure that we know when we've covered all of our costs and we can start making a profit. Okay? So the break-even point occurs when costs equal revenues. That's break-even. All right, we've been given two equations here. The cost equation is y equals 29x plus 1,000. The revenue equation is y equals 49x. How do we know what the break-even point is? It's when these two equations equal each other, okay? We could solve this as a system of equations, right? I would do this, y equals 49x, y equals 29x plus 1,000, right? And then I would just use the substitution method, right? Look, I would substitute one of these expressions for y into the other, right? Typically what I would do to solve this one, though, is I would say, oh, break even this point is when the cost equation equals the revenue equation, all right? But it is an application using the substitution method, so let's do it. So 49x will equal 29x plus 1,000, okay? To solve for x, we'll subtract that 29x from both sides. 49 minus 29, of course, is 20x. These are 0. So 20x equals 1,000. Divide by 20. And we see that x is equal to 50. And x is representing, what is x representing? Oh, I guess it's representing the pair of jeans. So x equals 50 pairs of jeans. I don't wonder why they call jeans a pair of jeans. It's not two jeans, right? It's just one pants that you're putting on. My mind wanders. All right, let's look at another application that doesn't necessarily lend itself to the framework for mixture problems. Okay, and this looks very similar to one that we've done in a previous lecture, doesn't it? Sam is 7 years older than Dean. In 12 years, the sum of their ages will be 51. We need to find out how old are they now. All right, so we're going to need to assign some variables for what we're trying to find out. Okay, let's see. Well, we need to know how old Sam is now and how old Dean is now, right? So why don't we let S equal Sam's age now, and we'll let D equal Dean's age now. That's what we're looking for. Often when we're solving an application problem, the variable is going to be the thing that we're trying to figure out. Well, let's see. It's not mixture, so we don't want a quantity and a value equation. But if we want to solve this with systems of equations, we're going to need two equations. So let's reread it and see if we can translate two equations. This first sentence says Sam is 7 years older than Dean. That usually means an equal, right? And we let S be the variable for Sam's age now. So Sam's age now is 7 years older than Dean, right? So if Sam is older than Dean, 7 years older than Dean, then Sam's age now is going to be Dean's age plus 7, right? So there's our first equation. S equals D plus 7. Because Sam is 7 years older than Dean. Well, there's an equation we can use. Now we need a second one, though. What does the second sentence say? In 12 years, okay, so 12 years from now, so if we add 12 years to their ages, then the sum of their ages is going to be 51. All right, so Sam's age now, S, plus 12 years, that's Sam in 12 years, right? And then Dean's age now plus 12 years, that's D plus 12, okay? And the sum of their ages in 12 years, so that's the S plus 12 plus the D plus 12. The sum of their ages in 12 years will be 51. So that's going to be equal to 51. And now I have a second equation. I think I want to simplify it a little bit. I don't really need these parentheses since everything's being added, right? So I could just say S, I could combine my like terms here, right? I could say S plus D, Sam's age now, plus Dean's age now, plus 24 equals 51. Equals 51. Okay. Well, I got two equations. I got that one, and I got that one, right? So I've got two equations and two variables. I can solve it. I think this one is going to be most easily solved with substitution again, right? Because I've got an expression for S right here that I can put into the second equation. That expression for S has D, so then I'll have an equation with just D's in it, okay? So instead of S plus D, we're going to substitute in the D plus 7 for the S, and we're going to say D plus 7 plus D plus 24 equals 51. Okay, let's combine some like terms. There's D's. 1D plus another D is 2D. And then we've got a positive 7 and a positive 24. When we add those together, that's 31, right? So 2D plus 31 is equal to 51. So solving for D, we're going to want to subtract 31 from both sides. Let's go up here to finish. Okay, so then 2D would be equal to 51 minus 31 is 20. And if we divide both sides by 2, we see that Dean's age now is 10 years old. What is Sam's age? Well, Sam is 7 years older than Dean, right? Or We can take that D and put that into the equation up here. D is 10. Let's use that one and put it in for right there. So then S is equal to 10 plus 7, or 17. Right? So right now we would say, so our solution then here would say that Dean is 10 years old, and Sam is 17. Okay. All right. A few more applications. Let's see. I don't really see anything that different. Well, let's just keep doing them anyway. All right. So what's happening here? Mixing nuts. Oh, this might be a mixture problem, right? Let's read it and find out. A store sells cashews for $6 per pound and pecans for $2 per pound. How many pounds of each should be mixed? Yeah, this is definitely a mixture problem. How many pounds of each should be mixed to have 25 pounds of a mixture that would sell for $3 per pound? All right, this is a mixture problem. We're going to write a quantity equation and we're going to write a value equation. Okay, so what are our variables going to be? Well, what are we doing? We're trying to figure out. We're trying to figure out how many pounds of each. Okay, so we're trying to figure out quantities. So why don't we let C equal the quantity of cashews in pounds. And we'll let P equal the quantity of peanuts in pounds. So then our quantity equation is going to be the number of pounds of cashews plus the number of pounds of peanuts equals the total number of pounds I have. We're mixing them to have 25 pounds, so that's my total. So C plus P equals 25. There's my quantity equation. All right, now let's write a value equation. If money's involved, the value equation usually is a monetary value equation. And look at this. I do have money involved, $3 per pound. So my value equation, how's that going to look? Well, let's see. Let's see, cashews contribute $6 per pound to the value. Okay, so $6 times the quantity of cashews plus peanuts contribute $2 per pound. So $6 times the quantity of cashews plus $2 times the quantity of peanuts is going to be my total value. What's my total value going to be? Well, I want to sell this mixture for $3 per pound, right? So it's going to be $3 times the total number of pounds. Do I know that? Yep, it's 25. It's 25 because it says that's how much we want to have and how much we want to sell. All right, so there's my value equation. I can simplify it just a little bit. Let me distribute that 3. So 6C plus 2P equals 3 times 25, or 75. Okay, this is solved just like the others. We'll use, I guess, substitution. Let me just subtract a P from both sides here and rewrite this quantity equation as C equals 25 minus P. Well, let's substitute that 25 minus P into the other equation for C. So that's going to go in right there. So then 6 times this new expression for C, 25 minus P, plus 2P is equal to 75. Okay, now we can simplify and solve for P. 6 times 25 is 150. And 6 times negative P is negative 6P plus 2P equals 75. Combine those P terms. So 150 minus 6P plus 2P is minus 4P. 75. Run out of room, so let's go finish it up here. Let's subtract that 150 from both sides. So then negative 4P equals 75 minus 150, or negative 75. And we'll divide both sides by -4. So then P, the quantity of peanuts, is 18.75. Speak. Okay, 18.75 pounds. What about the cashews? Well, you can substitute here, right? Look at this. Put this in there for P. Right there, in there for P. So cashews then is 25 minus 18.75, or 6.25 pounds. Okay, so mixture problems are not too bad if you can write a quantity equation and a value equation. If you can get to that, if you can set it up, and then you're good to go. Look at this application here. Can this be considered a mixture? Can this be considered a mixture problem? Let's see what's going on here. Connor has $200,000 to invest. A money market fund pays 6%, and a mutual fund pays 8%. Those are good interest rates. You won't be finding those today. Let's see, how much should he invest in each account to get an annual return of $15,000? What does an annual return mean? That's the interest. That's the interest that he needs to earn per year on this $200,000 he's investing. Well, this one's a little weird. Can we think about this as a mixture problem? I think so. I think so. What we're mixing here is investment interest rates. We're mixing interest rates, I guess. We're mixing investment types. Mixing investment types. So I guess we can write a quantity and a value equation. Let's see how this is going to work. Quantity, value. Okay, we're going to need variables. How much should he invest in each account? So I need to know how much is going to be in the money market and how much is going to be in the mutual fund. Well, they'll start with M. I guess I'll just let X equal the quantity of money in this case, but it's still a quantity. The quantity invested at 6%. And then we'll let Y be the quantity invested at 8%. So our quantity equation then is X plus Y, the amount invested or quantity invested at 6% plus the quantity invested at 8%, and that's going to equal that total quantity of money that we can invest. That's the 200,000. That's our quantity equation. Now the value equation, what's the value equation going to be? Well, the value here is the interest that this money is earning, right? So my value equation here is going to be an interest equation. Interest equation. All right, so let's see, 6%, 8%. Well, when we calculate with percentages, remember we have to move that decimal over. So 6%, when we move it over 2 places, becomes 0.06. 8% becomes 0.08. All right, so my interest equation or my value equation is going to be 0.06, the amount of interest that quantity invested at 6% earns. So that's 0.06x. Okay, and then so the quantity invested at 6% contributes that portion of the interest. The rest comes from the quantity that's invested at 8%, right? Or 0.08. Oops. 0.08 times Y being the quantity that's invested at 8%. And what does that need to total? It needs to total, it needs to be the interest, it needs to add up to the interest that we need, the total interest we need, which is $15,000. That's our annual return. So there we have our 2 equations, our 2 variables. We can solve. Substitution's been working nicely. Let's keep with that for now. So I don't know, maybe over here, I'll just subtract the X from both sides. So then Y is going to equal 200,000 minus X. Okay, let me substitute that into the second equation for Y, right here. Okay, so now 0.06x plus 0.08, and not y now, but this new expression for y, the 200,000 minus x, is going to equal 15,000. Okay, let's simplify and solve for x. So we'll distribute that 0.08. So 0.06x plus 0.08 times 200,000 is 16,000. Minus 0.08x. And that equals 15,000. Let's combine these like terms. 0.06 and negative 0.08 is negative 0.02x. Bring down that 16,000. So 16,000 minus 0.02x is 15,000. Okay, let's subtract that 16,000 from both sides. Out of room, aren't I? Let's go. Oh, so write this. Negative 0.02x equals negative 1,000. Then we divide both sides by that negative 0.02. Go up there and do it. And we see that x is equal to 50,000. Okay, so we're investing 50,000 at 6%. How much are we investing at 8%? Well, y is 200,000 minus x, right? So let's just substitute value for x in here. Y then is 200,000 minus the 50,000, or 150,000. Okay, so what's my final answer here? Let's see. I'm investing 50,000 at, what was x? That was 6%. So we want to invest $50,000 at 6%. And then y was 150, y was the 8%. So $150,000 at 8%. Okay. Stretching it a little bit, right? But that's a mixture problem. We're mixing investments, mixing interest rates, I guess, mixing investment types. So the framework worked very nicely for us. Let's look at another one. What's going on here? Let's see, we've got how much of each of a 25% alcohol solution and a 35% alcohol solution must be combined, okay, to get 20 liters of a 32% alcohol solution. Is it a mixture problem? I think so. I think it's a mixture problem. I think we're mixing alcohol concentrations. So I think it is a mixture problem. So I think that we're going to have a quantity equation and a value equation. Quantity, value. All right, so what are our quantities going to be? Well, we need some variables because we don't know, right? How much of each, 25% and 35%, maybe we'll just let x equal the quantity of 25%. Solution, and y can be the quantity of the 35% solution. So our quantity equation is we're adding some amount of 25% solution, that's x, with some amount of 35% solution, that's y. Okay, and the total quantity that we need, there it is 20 liters. So x plus y equals 20. There's our quantity equation. For the value equation, let's see. What is value going to be here? Value is going to be the alcohol concentration. The alcohol concentration, okay? So let's see. The value equation then, well, the x, that quantity contributes 25%. So 0.25x plus the y quantity, that's 35%, so 0.35y is equal to what? Is equal to 20? No, we're talking about alcohol concentration. So the alcohol concentration that I want to be equal to is 20 liters, but it's 32% alcohol solution, so it's going to be 0.32 times 20. All right, we can simplify that a little bit. So 0.25x plus 0.35y is going to be equal to 6.4. 0.32 times 20. There we go. Yep, now we can just solve the substitution the same as we've been doing. Works very nicely, doesn't it? Which one? Oh, it doesn't matter. Y is 20 minus x. Okay, let's put that into the second equation. So 0.25 times 20 minus x. Oh, no. I started to do that wrong, didn't I? 20 minus x is going in there for y. That one goes in this guy over here. There we go. This guy over here. Okay, so let's start that over. 0.25x plus 0.35 times is this new expression for y. That's the 20 minus x, right? And that's going to be equal to 6.4. Now we can simplify and solve for x. We'll distribute that 0.35. So 0.25x plus 7 minus 0.35x is equal to 6.4. Combine these like terms. So 7 minus 0.10x is equal to 6.4. Subtract that 7 from both sides. So negative 0.10x equals negative 0.6. Divide by the negative 0.10. X then is going to equal 6. All right, so what does that tell me? That's the quantity of 25% solution. What's the 30% solution? We're just going to put that 6 in there for x, right there. So y then is 20 minus 6, or 14. Okay, so we need, let's see, what's our liters, right? So we need 6 liters of 25% solution, and we need 14 liters of 35% solution. Okay, getting the hang of this? Not too bad. Practice makes perfect, remember that? All right, I'm going to just look at 2 more examples here. There's 2 more things I want you to see. This next one, it's actually only 1 more example, but this next one is a motion problem. Now, motion problems, most of the time if we have an application that involves motion, we want to solve that using the distance equation. And distance equals rate times time. Okay, that's always going to be true. And motion problems often use that equation in context. Now, motion problems are a little different than mixture problems. We aren't looking for a value equation and a quantity equation here. We're not doing that. The framework that probably works best to solve motion problems is to make a table of values based on the DIRT equation, or the distance equals rate times time equation. Okay, so if I make a table, if I make a little table of values with this, and we put distance in one column, and that's equal to rate times time, right? So if we put rate and time in the other 2 columns, then we can write our 2 equations on these next 2 rows here. Okay. Well, let's see. In this application, we've got an airplane traveling 1,120 miles in 7 hours. All right, so that's the first thing it's telling us. Okay, so it's 1,120 miles, but that's with the wind. Okay, you've probably heard the phrase tailwind, right? So when a plane is flying with the wind, it goes a little bit faster than it would if it was in still air. The wind helps it along and increases the rate. Against the wind, that same distance takes longer. It takes 8 hours. It takes longer because the wind is fighting the plane. You're flying into the wind. So the rate of that wind doesn't help the plane, but the rate of that wind slows that plane down a little bit compared to the rate that it would fly in still air. All right, so what do we need to find? The rate of that plane in still air, if there was no wind, right? And then we also want to find the rate or velocity of the wind, Okay. Technically, velocity means direction, so we're probably just looking for the rate or speed of the wind here. All right, so we want to try to write two equations, and we want to base on this distance equals rate times time. Well, the distance that the plane flies with the wind as well as against the wind is the same. It's 1120 miles. So I can fill in that distance here, 1120. That's the distance it flies where it's going to with the wind and when it's coming back against the wind. All right, so my two equations here, my first equation, maybe we'll say this is with the wind. Okay, and then my second equation might be against the wind. Where we're fighting the wind. Okay, with the wind, we're told that it took 7 hours, right? So time here is going to be 7. Against the wind, it takes 8 hours. Okay, so my time in my against row is going to be 8. Now I've got to think about this rate, or this speed, if you will, the speed of this plane. Now, when the plane is flying with the wind helps it, right? So it's like there's two different rates here, right? We might say R is the rate of the plane in still air with no wind, right? And then we might say W is the rate of the wind, right? Because, wind has speed. It might be 5 miles per hour, might be 10 miles per hour. Okay, our rate here is our speed. I'm calling it velocity, but technically velocity means direction, so I don't know that that's the right term there. So how can I identify the rate with the wind? Well, it's going to be the rate of that plane in still air plus the rate of that wind, as the wind is pushing that plane along. There's a tailwind going on, right? But against the wind, the rate that plane actually flies at would be the rate of the plane in still air minus the rate of the wind. The wind is fighting that plane. It's slowing it down a little bit. Okay, once we've filled in this table, then we can simply write our two equations. Distance equals rate times time, right? So my first equation here is going to say distance, 1120 miles, equals rate. This rate is R plus W. I don't know what it is yet. It's the rate with the wind. And the time, rate times time, the time is 7 hours. So that's the first equation. The second equation, that same distance, 1120, against the wind, that wind is fighting it. So the rate here is going to mean R minus W times, and of course it takes longer, 8 hours. Times 8 hours. Okay, so there's our two equations. Now we can simplify this. Let's distribute the 7 here. Let's distribute the 8 here and simplify this. When we simplify it, we get 1120 equals 7R plus 7W, and 1120 equals 8R minus 8W. Two equations with two variables. Now we can solve it using either substitution, elimination. We could try graphing it. I'm not going to graph it, though. I think elimination is going to be the best method to use here. There's a positive and there's a negative. If I solve for R, it's going to be in fractions. If I solve for W, I think I'm just going to, I don't want to do substitution. I think I'm just going to do the addition method or the elimination method. And this time though, I'm going to need to multiply both of these equations by something, because I can't think of something I can multiply one equation by where, and then when I add them together, the variables are going to add out. I think what I'm going to have to do here is multiply that first equation by 8 and multiply that second equation by 7, because then I'm going to have a positive 56W and a negative 56W, and the W's will add out. The W's will add out. All right, so let's distribute those and rewrite these. I'm doing here with the 7s as well. Okay, so now I'll have 8 times 1120. That's 8960 equals 8 times 7 is 56R plus 56W. And my second equation, 7 times 1120, I have 7840 equals 56R, 7 times 8R, minus 56W. Okay, now when I add them together, the W terms add out. All right, so 8960 plus 7840. Oops, isn't right. I didn't do that right. Let's try it again. 8960 plus 7840 is 16,800. 56 plus 56 is 112 R. Divide both sides by 112. I'm going to have that rate of that plane in still air. 16,800 divided by 112 is 150. So I've got that rate of that plane in still air, but I need to know something else too. I also need to know the velocity of that wind. Well, how am I going to find the velocity of the wind? Let me just plug it into one of the equations. Let me just plug that R into one of those equations. So which one can I plug that into? Doesn't matter. Here, I'll use that bottom equation. It's the closest one. I'll just put that 150 in there for R. Okay, I'm kind of out of room. Maybe I'll just move this up and write it down here. All right, so 1120 then is going to be equal to 8. Instead of R, we use the 150. 8 times 150 minus 8W. And this is going to tell us, when I solve for W, the rate of that wind. Okay, so 8 times 150 is 1200. So 1120 equals 1200 minus 8W. When I subtract that 1200 from both sides, 80 equals negative 80, equals negative 8W. Divide by the negative 8, and W equals negative 8 divided by negative 8, or 10. So there we have it. We have our solution. The rate in still air, so the rate of the plane in still air is 150. What are my units here? Miles per hour. And the rate of the wind is 10 miles per hour. Okay? And that ends the lecture on systems, linear systems.